Dihedral Effect. Every pilot knows that yawing an aircraft also causes it to roll. This is valid for either type of aircraft. It doesn't matter if it is a turboprop or a jet, a straight wing or a swept wing. This is called the dihedral effect. You know, dihedral is the angle of the wing with respect to the horizontal line, as seen in the picture, which causes an interesting aerodynamic effect. If any bank angle is introduced, the consequent side slip causes the wing to roll back to wings level. This is caused by the aircraft sliding toward the lowered wing, which increases its angle of attack, while the other wing has its angle of attack decreased, resulting in a rolling moment and approximately proportional to the dihedral angle. Wing sweep also produces a rolling moment due to side slip, caused by the change in relative sweep of the left and right wings. Due to wings being swept in a high-speed jet, the effect is normally stronger than in turboprop aircraft. See how it works. When the aircraft is yawed, the inside wing is slowed down, and the outside wing is speeded up, therefore unbalancing lift in each wing separately, resulting in aircraft roll. The outside wing produces more lift because it is effectively less swept, while the inside wing loses lift because it is more swept. This contributes to further unbalanced lift, and rolling is exacerbated markedly, adding to the actual geometric dihedral. Consequently, pilots must be aware that rapid application of large rudder displacements or rapid application of asymmetric thrust may create control difficulties. Rudder and asymmetric thrust inputs must be made carefully and smoothly. Care is also necessary to overcome the dihedral effect during uncoordinated maneuvers, such as during approach and landing with turbulence or crosswind. Stall characteristics. The simple task now is to answer how different is stalling a propeller aircraft and a jet. The difference lies in the planform of the wing. Compare the straight wing lift distribution with a swept wing lift distribution. Lift on swept, untwisted wings is concentrated on wing tips rather than the concentration at the root in a straight wing. Since the wing stall is started in the vicinity of the highest lift coefficient, the swept wing has a tendency to develop a stall pattern that begins at the tip. If an actual wing were allowed to stall in this fashion, aileron buffet would occur, and the wing would drop. No nose-down moment and very little aileron effectiveness would be felt. When sweep back and taper is combined in a wing, the tip stall tendency is further aggravated. The straight wing exhibits low lift at the tip and high lift at the root, which contributes a lot for favorable stall pattern characteristics, adequately signaled by the stall warning buffet, adequate aileron effectiveness, and the usual strong nose-down moment. There are several means of correcting the tip stall tendency. The Embraer jets make use of wing geometrical twist to decrease the local angle of attack at the tip. In addition, the airfoil section is varied throughout the span to an airfoil with delayed stall development. Another feature used in the Embraer jet family are those interesting vortilons installed at the wing tip. They delay tip stall even more, so the jets have full roll control throughout the normal operating range down to stick pusher speeds. The variable incidence stabilizer. There is one other important feature of flying faster I would like to point out. On a fixed-tail aircraft, flying at low speeds, the elevator needs to be commanded up, while flying at higher speeds, it needs to be commanded down. If the speed range at which our aircraft flies is too extended, considerable elevator deflection would be necessary, requiring large displacements of the control surface to provide adequate longitudinal control. The solution for this case is the introduction of the variable incidence stabilizer. The variable incidence stabilizer is quite effective because it can be moved to a large deflection, which for itself is a good reason to manage its operation with care. A mistrimmed takeoff may result not only in higher than normal forces, but also insufficient control authority with full elevator deflection. Therefore, before takeoff, set the stabilizer to the required setting according to the CG position. We have come to a point in our presentation where we have gathered fair knowledge to give a full treatment to one of the end products of this video, the recommended flight techniques to approach and land a jet aircraft. Just to recall what we have said till now, a jet may be worse than a propeller aircraft in the following ways: the poor acceleration response of the jets in low engine rotation, the poor lift at low speed characteristic of the jet, the potential hazard of flying at the backside of the drag curve, the absence of propeller slipstream in preventing stall and producing extra lift. Put all these facts together, and you will see how potentially more difficult it can be for the pilot of a jet when making an approach and correcting inadvertent errors. Developing high sink rates is a unique problem and represents a potential hazard in jet aircraft. However, with the proper understanding of these considerations, neither one of these tasks is difficult. Remember that basically you need more lift to get out of the increased rate of descent and go back to the proper flight path. And you can get lift by increasing angle of attack or airspeed. To increase angle of attack, your airspeed must be acceptable, or the extra pitch will take you to the backside of the drag curve, and the resulting sink rate will be higher. The final solution is thrust, but it may take a lot of time, so this option is practicable only at a safe altitude. To keep away from the potential development of high sink rates, fly the stabilized approach concept. The stabilized approach. When the whole approach is properly controlled, the possibility of something going wrong is drastically minimized. Avoid power-off approaches. Recall the poor acceleration response of your jet aircraft and set power with judgment. Anticipate the need for more thrust should airspeed decrease, but don't leave power up for too long or the aircraft will go fast again. Keep thrust in such a value which allows the engine to accelerate to a higher RPM if necessary. And it is also good to keep the airplane in the approach path. In the Embraer regional jets, a typical target N1 is 60%. And if you keep it within plus or minus 5%, it will be good. Keep the airplane in a stable glide path. And remember that large changes in airspeed will require also proportionally large changes in power and attitude. Variations in the target airspeed must be kept within a range of 5 knots. Prior to reaching the outer marker, or at least 3 nautical miles away from the runway threshold, the airplane should already be configured for landing in a stable glide path with landing flaps and gear locked down. For a normal glide path of 2.5 to 3 degrees, the resulting rate of descent is about 650 to 800 feet per minute. Rates of descent in excess of 1,000 feet per minute should be avoided. The use of the flight director for ILS-guided approaches and VASIS and PAPI for visual reference is recommended. If possible, avoid sidestep maneuvers at less than 3 nautical miles away from runway threshold. Plan the touchdown point at the 1,000-foot runway marker. Do not permit the airplane to float during the flare. Using a normal flare technique as the airplane approaches the touchdown point, reduce the rate of descent by increasing the nose-up attitude and slowly reduce engine power in order to achieve idle as the airplane touches the runway. Normally, a 2-degree or 3-degree pitch-up change is required to reduce the rate of descent during the flare. Flying the stabilized approach concept is a goal that sometimes cannot be reached due to emergencies or ATC requests. To give you support to fly at that desired concept, let's discuss some interesting approach conditions. Non-precision approaches.